3.5 billion miles from Earth lies one of the most captivating objects in our solar system. It's a tiny, icy world with the strangest atmosphere ever studied. It may have giant geysers, underground oceans. There's even a small chance it has primitive life. It's changing the way we look at Earth and our solar system. This is the former planet known as Pluto. Pluto sits on the edge of our solar system, 3.5 billion miles from Earth. Remote but not forgotten, for generations of school children, Pluto is the 9th planet. But on August 24th, 2006, Pluto lost its planetary status. It was reclassified as a dwarf planet.
Pluto doesn't care what we call it. It doesn't care whether we call it it's going to be the same object whether we call it a planet or a dwarf planet or a minor planet.
Pluto has all of the characteristics of the other planets. In the same way that a chihuahua is a dog, just smaller. Dwarf planets are planets. They're a smaller variety.
Pluto sits on an exciting new frontier of space exploration. A state-of-the-art spacecraft is heading towards it at around 1 million miles a day. Scientists hope that it will shed new light on the formation of the solar system and even the birth of our own planet.
Every time we take a spacecraft and go by a new body, it turns into an entire world that is filled with fascinating phenomena that we would have never understood before.
The fact that Pluto is so far away, it's so small, it's so dim, and may represent now a whole new swath of real estate worth of objects, tells us that Pluto has a lot in store for us to learn about it.
Our story starts with Pluto's discovery. By the early 20th century, 8 planets have been discovered. Many assume that Neptune is the outermost. But astronomer Percival Lowell is convinced there is another planet out there, a massive planet whose gravitational pull is disturbing Neptune's orbit. He calls it Planet X, but it proves elusive, and for good reason. The giant planet theory is wrong.
The original motivations for searching for Pluto were based on bad data, basically. They just didn't have enough information then and good enough data to really solve this problem.
By 1929, astronomers at Lowell's Observatory outside Flagstaff, Arizona, had been searching for Planet X for 14 fruitless years. 23-year-old amateur astronomer Clyde Tombaugh joins the team and is given the painstaking task of comparing vast numbers of star-like objects. Tombaugh captures the images onto large photographic plates using a 12-inch telescope, small by today's standard. He's looking for tiny points of light that have moved across the night sky. Stars remain fixed while planets move. Tombaugh continues the search for over a year. Then, examining the plates taken on the 23rd and the 29th of January 1930, a faint object catches his eye. Flicking between these two images, he sees that the object appears to have moved. He checks and rechecks, making sure it isn't a comet or a blemish on the plate. It seems the young astronomer has discovered the astronomical Holy Grail, Planet X.
He also was extremely lucky to be looking at the right part of the sky at the right time. And of course, he had very keen eyes and skillfully able to pick out that small object as it moved across the sky.
Even though the giant planet theory turned out to be wrong, Tombaugh still found a planet. The new discovery is headline news. The planet is named Pluto, after the Greek god of the underworld. Based on their original miscalculation, they believe Pluto is bigger than Earth. Pluto officially becomes the solar system's 9th planet. Today, over 70 years later, Pluto is still pushing Lowell's modern telescopes and leading astronomers like Mark Buie to the very limit of their abilities.
Even with modern day tools, it's a difficult job to find these objects, and you have to look at a lot of sky, a lot of data, use the computers, use all these tools, and we work down at the very limits of what our data and our telescopes can do.
For decades, even the most basic questions about Pluto remain shrouded in mystery. And the most basic of all, its size. The breakthrough comes in 1978 with the discovery of Pluto's largest moon, Charon. It was a stroke of luck, as no one thought Pluto had any bodies nearby. Astronomers were able to estimate Pluto's mass by looking at its gravitational influence on Charon.
Now we know what the mass of Pluto is, and all of a sudden it goes from this vague, poorly known place to now you know something about it and can start putting it in context.
The results are surprising. Pluto is not larger than Earth. In fact, it's smaller than our own moon. Side by side, Pluto and Charon only cover the width of the United States. But for astronomers, the biggest mystery was why Pluto appeared to be on its own. In 1951, Gerard Kuiper theorized that Pluto was a remnant of a once massive belt of objects circling the outer solar system. This region of space became known as the Kuiper Belt.
Kuiper predicted a huge empty space where we see the Kuiper Belt. He thought that Pluto was a massive body that would have swept out all the objects there. And in fact, that's not the case at all.
Back then, Kuiper didn't know that Pluto was too small to have had this dramatic gravitational effect on other bodies. Maybe there was a belt of icy objects out there, just too small for them to see with their limited telescopes.
By 1985, it did seem kind of odd to me, and to other people, I think, that the outer solar system would be a very empty place, where essentially nothing was known except for Pluto.
Mauna Kea, Hawaii. In 1988, Professor David Jewett of the University of Hawaii's Institute for Astronomy begins a dedicated hunt for another object beyond Neptune. Despite harnessing the latest digital technology, the task of looking for a tiny asteroid-sized object at the far reaches of the solar system is a daunting one. A bit like finding a grain of rice on a mountainside, as Jewett demonstrates.
To give you an idea for the scale of the Kuiper Belt relative to the orbits of the planets, I've laid out the solar system using various kinds of fruit and vegetables. So we have a ball to represent the sun. Next to the sun, which is the center of the solar system, we have the rocky planets. So we have to go out to 5 astronomical units, 5 AUs, to find Jupiter, the biggest thing in the solar system except for the sun. Then we go out from Jupiter is Saturn, located at 10 AU. Out from Saturn is Uranus at 20 AU. Uranus is the first of the ice giant planets, and Uranus has a near twin. It's called Neptune. Neptune is over here at 30 AU. And then just beyond Neptune comes the famous Pluto, represented here by a tasty macadamia nut. And Pluto moves in and out from the sun, but it's roughly located at 39 AU. So we'll put that back where we find it. Kuiper Belt starts roughly at the orbit of Neptune and goes out to larger distances. So we can represent that by grains of rice from this bag, which I'll drop on the ground, These are Kuiper Belt objects falling in space, and here they go, but in fact they go very far out. They go out in this direction, and in fact it goes out so far that I can't throw it far enough. It goes out to the hill in the distance, far beyond me.
But in 1988, all this is speculation. It's just a theory. There's no hard evidence of other objects in the Kuiper Belt. Dave Jewett continues believing there have to be more Kuiper Belt objects out there, somewhere. For 4 years, he toils in the thin air of Mauna Kea's high-altitude observatories. He has no idea how big or bright any of the objects might be. Then in late November 1992, he and his colleague Jane Liu spot a faint moving dot in the sky.
It was a very, very definite object, far above the noise, far above the threshold of uncertainty. We're completely sure that we found the first really slow-moving thing in the solar system since Pluto.
And it's small, just 140 miles across. Its diameter is just a tenth of Pluto's.
If we were able to find one body in 0.1% of the sky, which was the case, then we knew there must be something like 1,000 times more objects than we'd found.
Jewett's discovery has astounding implications. Now astronomers know there are potentially thousands of icy bodies, escapees from early planetary formation, orbiting out beyond Neptune. And Pluto is just one of many. Perhaps Pluto is not a planet after all. The discovery of thousands of objects in the Kuiper Belt opens up a whole new realm of planetary possibilities. Pluto no longer marks the edge of the solar system. There are hundreds of objects in the Kuiper Belt waiting to be identified, and astronomers are scrambling to find the great prize, an object bigger than Pluto. In 1998, Professor Mike Brown at the California Institute of Technology joins the hunt. At the Palomar Observatory in Southern California, Brown's team embark on an extensive search.
We had started this project of scanning the skies 7 years earlier, and with the idea that we wanted to see if there was something bigger than Pluto out there. We thought there just had to be.
Unlike Tombau's manual method, the team uses a computer-controlled telescope with digital cameras to take hundreds of images across the whole sky.
Clyde Tombaugh used photographic plates, and he would take 2 photographic plates and compare them and look for something that moves. We now use the digital cameras instead, and the computer does most of the work that Clyde Tombaugh did.
On October 21st, 2003, the computer records a snapshot of space and gives it a code: 2003 UB313. But with such a backlog of images, 2 years pass before Brown has a chance to review it. Like Tombaugh, it's now down to his skill and judgment to spot one significant object among thousands.
And suddenly this big bright object appears on my screen, and my very first reaction, what did I do wrong? Something must be wrong here. This can't be right. And I checked everything, and realized, no, this is really there. And I immediately picked up my phone and called my wife and said, hey, I just found a planet.
2003 UB313 is around 70 miles wider than Pluto. And though it's 3 times further out than Pluto, it's one of the brightest bodies in the Kuiper Belt. Astronomers call it Eris.
We knew immediately, once you start discovering other objects beyond Neptune and look at the distribution of their sizes and the rate at which you're discovering, it was just a matter of time before you would find one larger than Pluto. And in fact, that's happened.
I never actually really thought we were going to find that one bigger than Pluto, so it was sort of a fun moment.
For Brown, Eris is the discovery of a lifetime. For Pluto, the implications are serious. No longer alone, and not even the biggest or brightest body beyond Neptune, can we still call Pluto a planet? One of the first to publicly question Pluto's status was director of New York's Hayden Planetarium, Dr. Neil deGrasse Tyson.
We first opened to the public in the year 2000, not including Pluto among the ranks of the other principal objects in the solar system. And we got raked over the coals by the New York Times had a page one story saying Pluto not a planet, only in New York. Okay, and then I got like hate mail from third graders, ever since.
Tyson leaves Pluto out from the display because it doesn't fit into his two main planetary categories: the inner rocky planets and the outer gas giants.
Pluto's always been a curious object, primarily because we've known so little about it.
Defining a planet is not as simple as it seems. Take Neptune's moon Triton, for example. Although it's 40% bigger than Pluto, Triton is just a moon. After much deliberation, the International Astronomical Union came up with a new definition. Planets now have to meet three basic criteria. They have to have sufficient mass for gravity to contract them into a sphere. They have to orbit the sun and not some other body, or else they would be moons. And lastly, they have to clear the material around their orbit. Unfortunately, Pluto fails to meet one of the criteria. It does not clear the neighborhood around its orbit. On August 24, 2006, Pluto is reclassified as a dwarf planet.
The word planet hasn't been defined since ancient Greece. Back then there were 7 planets: Mercury, Venus, Mars, Jupiter, Saturn, the Sun, and the Moon. And it was never redefined to accommodate our new understanding of the solar system.
Pluto may have lost its planetary status, but it hasn't lost its intrigue. The more scientists learn about Pluto, the stranger its story becomes. Unlike all the other planets, Pluto's surface is covered with exotic ices, such as frozen nitrogen and methane. There are at least 3 moons orbiting Pluto, a planet 2,000 times less massive than Earth. And Pluto's eccentric orbit is more like a comet's. For almost 60 years, it was also impossible to tell whether Pluto had an atmosphere. And when scientists finally get a chance to look, they discover something remarkable. Pluto's atmosphere is unique in the solar system. It's causing the planet to shrink. Pluto, once an isolated planet, the 9th in our solar system. Now stripped of its planetary status, Pluto is just one of thousands of icy bodies in the solar system's furthest reaches. It might not be alone, it might not be a planet anymore, but Pluto is still intriguing. And as scientists unlock the mysteries of Pluto, they're discovering a world full of puzzles and surprises. Astronomers figured out that Pluto was cold and that its surface was encased by ices, but for 58 years, they couldn't tell whether it had an atmosphere. No telescope on Earth was powerful enough to confirm this basic phenomenon on an object 3.5 billion miles away.
Even using the most powerful telescope available to astronomers, the Hubble Space Telescope, which is a fantastic instrument, Pluto just looks like a barely resolved, very pixelated object. We just can't see much detail.
On June 9th, 1988, NASA's Kuiper Airborne Observatory takes to the skies. Astronomers board this specially equipped high-altitude plane on a journey to the Earth's stratosphere. Their mission is to search for evidence of an atmosphere on Pluto by observing a strange celestial phenomenon. The only way to identify an atmosphere on a remote body like Pluto is to observe it during a type of eclipse known as an occultation. When a celestial object, like a moon or a small planet, passes in front of a star, starlight is sharply cut off if there is no atmosphere present. But if the body does have an atmosphere, the starlight behind it gradually dims as the body passes in front. On board the plane, high-powered telescopic instruments record the critical moment.
Wow, okay. I think that thing has an atmosphere, guys. Yep, atmosphere.
Pluto has an atmosphere. It's similar to Earth's, but extremely thin.
Pluto's atmosphere has many of the same chemical constituents as the Earth's atmosphere, but there's very little of it. If we took all of Pluto's atmosphere and we cooled it down even further than its current cold temperature, and it collapsed onto the surface as a frost or snow, we'd have snow up to the kneecaps.
But how does Pluto have an atmosphere under these frozen conditions? The answer turns out to be linked to its eccentric orbit. Most planets take a roughly circular route around the Sun, but Pluto follows an extreme elliptical path. Its orbit carries Pluto as close to 2.9 billion miles from the Sun and as far out as 4.6 billion miles. By contrast, Earth's distance from the Sun varies by just 3 million miles. Pluto receives almost 3 times more sunlight at its closest point to the Sun than at its furthest point. As it moves towards the Sun, Pluto's surface ices turn into gases. The result is a unique atmosphere. It comes and goes. Mark Buey of the Lowell Observatory in Flagstaff, Arizona, explains that Pluto's strange atmosphere is, in effect, turned off and on by the Sun.
This is a little bit like what the atmosphere of Pluto might be like when Pluto is closest to the Sun. And then as the Sun goes away from Pluto, this is what happens. We're going to stick this balloon into this really cold liquid, and the balloon starts to collapse and shrink and get smaller and smaller and smaller as the pressure of the gas inside goes away. And hold it here long enough, and now I have a totally collapsed balloon. Now you'll notice as I pull it back out, it's starting to warm up again. There's actually liquid air inside there. And the gas starts to expand and swell up. And this is kind of what happens with Pluto's atmosphere, we think, over the course of its year. At perihelion, or when it's closest to the Sun, you have this big atmosphere, and then when it gets furthest away from the Sun, the atmosphere shrinks and could maybe even disappear entirely.
No other known body has such a radically fluctuating atmosphere. And the more scientists study it, the stranger it becomes. Fran Bagenal, professor of astrophysical and planetary sciences at the University of Colorado, thinks that Pluto looks like a comet because it has an atmosphere that leaks into space. Pluto's gravity is so weak that its atmosphere stretches hundreds of miles above the surface.
Similarities with the comet are that the weak gravity of Pluto allow the atmospheric gases to escape. And so, as Pluto gets closer to the Sun, you have greater evaporation and more material escapes. Indeed, it looks very much like a comet in that respect.
When a comet travels towards the Sun's heat starts to affect its icy surface. Ices turn into gases and are blasted away, giving the comet its distinctive tail of ionized gas and dust. Although Pluto doesn't release dust like a comet, it does leak up to half a ton of atmospheric gases every second. And this leads scientists to a startling conclusion. Pluto must be shrinking. Each time it heats up, it gets a little smaller. During our solar system's lifetime, as much as 18 miles of Pluto's terrain may have been lost to space.
And so as a result of this, we expect there to be a considerable variation in the surface, hills and valleys that have evolved over the age of the planet.
Hidden for decades, Pluto's strange surface is obscured to even the most powerful telescopes. But there is a special type of device that can bring it into focus. The infrared spectrometer reads the distinctive reflective signature of Pluto's surface. Using this technology, scientists can piece together a remarkable picture of the strange world of Pluto. Spectrometers tell us that Pluto's surface is covered by exotic ices. Temperatures on Pluto drop to a chilling minus 396 degrees Fahrenheit, so that nitrogen, methane, and carbon monoxide exist as frozen solids. The gases we breathe, see through, and move through on Earth make up Pluto's rocks, plains, and hills. Astronomers think that around 30% of Pluto is made up of ices. Beneath the exotic ice-covered surface sits a water-ice mantle. But is Pluto just a frozen world? As scientists investigate this puzzling dwarf planet, an intriguing possibility emerges. Could there be an ocean hidden beneath its surface? Could the existence of ice and liquid water on Pluto provide further evidence that the Kuiper Belt was a source of Earth's water? Scientists believe that Pluto-like worlds may have played a fundamental role in bringing water, the vital ingredient for life, to Earth. In the outer solar system where the sun's influence is weak, water ice is abundant. But could Pluto also have liquid water? Professor Bill McKinnon of the Washington University in St. Louis thinks so. He believes that beneath Pluto's frozen surface, there could be an ocean. McKinnon believes that water on Pluto could exist in liquid form due to the presence of ammonia, which acts like antifreeze. If he's right, water could remain liquid at temperatures far lower than those of the Antarctic.
Bodies like Pluto can actually have oceans. Not oceans on the surface like on the Earth, but oceans down below. And I have basically Pluto right here in this glass, and I can add the water and something like ammonia that would be inside Pluto.
Add ammonia to water, and the freezing point plummets to nearly minus 142 degrees Fahrenheit.
And to make it look more oceany, although we have no idea what the color of Pluto's ocean would be, we'll add some food coloring. Now out there in space, you're a long way from the sun, so it's cold. And so the top will freeze, like on a lake or in the Arctic, and you'll actually start freezing from the top down, and you'll make a thicker and thicker layer of ice, and I'll start it off by adding some ice at the top, which will float. And then, because we can't actually go into deep space, we'll put it in the freezer. But I put an earlier version of this a couple of hours ago, and this is sort of what you'd actually get. You'd actually see an icy layer floating on, I can jiggle it a little bit, a liquid layer that actually won't freeze.
After 2 hours in the freezer, the ammonia keeps the water liquid. But turn the temperature down below minus 142 degrees, and even ammonia-rich water freezes. On Pluto, surface temperatures are a mind-numbing minus 390 degrees Fahrenheit. At temperatures this low, every drop of water should freeze. So for water to remain liquid under the surface, there must be another force at play. a force that scientists believe lies deep inside Pluto's inner rocky core. Here there may be radioactive substances which generate heat as they decay. This heat could raise Pluto's subsurface temperatures to the critical level where ammonia-rich water can exist. It's a tantalizing theory, because whether in liquid or frozen form, the presence of water on Pluto and its Kuiper Belt neighbors could hold the key to one of our planet's greatest mysteries: the origin of its oceans. One popular theory suggests that comets, which are rich in water ice, may have delivered water to Earth. But Dave Jewett thinks comets may not be the only source of Earth's oceans. Jewett believes Pluto-like bodies in the Kuiper Belt may also have played a part. It would take roughly 1 billion average-sized comets to deliver Earth's water, or one single ice ball 600 miles across. No comet this large has ever been discovered. But in the Kuiper Belt, there are between 50 to 100,000 ice-rich objects larger than 60 miles in diameter, and dozens at least 600 miles across. At the dawn of the solar system, astronomers estimate that the Kuiper Belt was around 100 times more massive than it is today. Sometime in the past 4 billion years, the Kuiper Belt has shrunk.
Several tens of Earth masses, even up to 100 Earth masses of stuff, originally was present in the Kuiper Belt and then was lost by some process that remains mysterious.
Could this loss coincide with the creation of oceans on Earth? This is Neptune, the 8th planet and the Kuiper Belt's closest gas giant. Computer simulations show Neptune's huge gravitational field may have dislodged Kuiper Belt objects, sending them spiraling toward the Sun. Parts of them may have collided with Earth.
We know there was a period of time when there was just stuff slamming in all over the place. And that had to hit the Earth too. It's possible, entirely possible, that those objects were Kuiper Belt objects, which are full of ice and water. Most of the water is hanging out in the outer solar system, and all the rocks are in the inner solar system, but maybe by these stirring events, you can kind of bring these two areas together.
If the theory is correct, objects like Pluto in the Kuiper Belt played a part in delivering Earth's water, vital to all life as we know it. Pluto is slowly yielding its secrets, shedding new light on our solar system. But incredibly, almost 80 years after its discovery, we still don't really know what Pluto looks like. Despite powerful modern telescopes, there are no detailed images of Pluto. These, taken in 1994, are the clearest to date. They were captured by Hubble, the space telescope that escapes the distorting interference of Earth's atmosphere. The largest point of light in the center is Pluto. Its largest moon, Charon, is next to it. To construct a global map of Pluto's surface, Mark Buey turns to Hubble's infrared images.
Each one of these images represents one picture taken with the Hubble Space Telescope. You stitch all those pictures together into a uniform map, which then I can manipulate and make it look like a globe.
This composite globe shows a reddish surface with patches of light and dark, evidence that Pluto has a varied landscape. At the solar system's outer limits, beyond the reach of even the most powerful telescope, Pluto remains shrouded in mystery, but not for much longer.
You either need a bigger telescope or you gotta go there. And so, we're going there.
Right now, a sophisticated spacecraft is racing towards Pluto at around 1 million miles a day. It's ETA 2015. January 19th, 2006. The Atlas V rocket blasts off from Cape Canaveral, Florida. On board, the New Horizons spacecraft. It's on a 9-year journey to Pluto and the Kuiper Belt. This is a voyage into the unknown. Since NASA's inception in 1958, its missions have provided stunning pictures and vital scientific information about our solar system. Some have even involved robotic landing vehicles to examine and explore these new worlds up close. NASA has sent spacecraft to every major body in the solar system, except Pluto. Pluto is still waiting to be explored. In the first ever image of Pluto taken almost 80 years ago, the planet appears as a tiny pinprick of light, no brighter than a distant star. Even the latest images, captured by the Hubble Space Telescope, show Pluto as just a blurred ball of light.
Pluto is so far away and so small that Hubble's capacity to see detail is greatly limited.
To get a sense of what it's like to try and see Pluto, the best thing to do is to think about if you were to look at a ping pong ball, someone was to carry it 25 miles away.
An important clue to Pluto's appearance comes from data gathered by another mission to the outer solar system. In 1989, NASA's Voyager 2 skimmed past one of Neptune's 13 moons, the mysterious Triton. This flyby provided astronomers with a tantalizing glimpse of what Pluto might look like.
This icy moon, this large icy moon, that's very much a companion to Pluto, similar size, similar part of the solar system, and maybe had a very similar origin.
Astronomers theorize that many billions of years ago, Neptune slung Pluto outwards and dragged Triton towards it, taking it captive as a moon.
Triton is just like Pluto, but it got captured by Neptune billions of years ago. If we were to fly over Pluto, we would see impact craters and volcanic calderas or collapsed craters and maybe even active venting or plumes, because we see these things on Triton.
Triton's strange landscape suggests that Pluto could be a dramatic place. And on Triton, the most dramatic features of all are geysers. Voyager 2 captured these remarkable images, evidence of geysers that last for up to a year and spurt gas and dust up to 5 miles high. If there are similar geysers on Pluto, astronomers predict that they would be driven by the sun. Although the sun is over 3.5 billion miles away, its heat may still have the power to affect the ice beneath Pluto's surface, turning it into gas. Pockets of subsurface gas would build up and eventually burst through Pluto's frozen surface as geysers. Will Grundy demonstrates how even a small increase in temperature produces a large geyser.
Okay, we're going to put liquid nitrogen into this plastic bottle, and it's very cold at 77 degrees above absolute zero. So as soon as it comes into contact with the hot environment here with the sun shining and the warm air, it starts boiling like crazy. And as it boils, it's going up into gas, giving off a huge amount of gas. And as soon as I screw the lid on, the gas has nowhere to go except up the tube in the lid and out through this cooler full of ice to form our simulated geyser. And here it comes. On the surface of Pluto, don't know what the scale of those geysers would be, whether they'd be very small like this one or maybe a kilometer tall.
Such mysteries will be solved on New Horizons' arrival in 2015. The spacecraft's camera has already been tested 6 months into its epic journey, capturing perhaps the greatest volcanic eruption ever witnessed in space. 76 years after Pluto's discovery, and after 17 years of research and development, NASA's New Horizons spacecraft sets out for Pluto. Traveling at around 1 million miles a day, it's on a 9-year, $700 million journey to reach Pluto and reveal its secrets. New Horizons chief scientist is Hal Weaver.
Yeah, where we are right now is mission control for the New Horizons mission to Pluto. This is where we watch all of the activities that are occurring on the New Horizons mission. We have over here to the left a depiction, a software prediction of exactly where the spacecraft is, where it's pointed. You know, we're following it on its path to Pluto.
In early 2007, New Horizons passes Jupiter, using the planet's intense gravity to boost it toward Pluto. It took the opportunity to test its camera on Jupiter's largest satellite, Io. The results were spectacular. This footage, captured by New Horizons' long-range reconnaissance imager, shows the actual eruption of a volcano on Io's surface.
We were just lucky and happened to catch it when one of the major volcanoes was active. It had spectacular plumes, debris, volcanic debris was flying up for a couple of 100 miles above the surface.
It's a stunning but short-lived encounter. New Horizons soon leaves Jupiter behind. Traveling at over 8.5 miles a second, it's the fastest spacecraft ever launched. It's going so fast that after its 9-year journey, New Horizons will only have a day and a half to see Pluto close up before disappearing deeper into the Kuiper Belt.
And that's great for getting there early. But on the other hand, of course, that means that everything is really sped up as we fly by, because unfortunately, we can't just go to Pluto, put on the brakes and stop and hang around for a while. Roughly 3 months out, we're going to have resolution that's better than Hubble, and then it just gets better and better and better as we get closer and closer. But for those last 24 hours where we have this really high spatial resolution where we can see football field-sized features on the surface of Pluto, that all happens very quickly. We're just going to fly by and then just by Pluto and on deeper into the Kuiper Belt.
With such a short window to capture data, the team must test and retest the instruments throughout New Horizons' 9-year journey.
Every year, for about 2 months, we're going to wake the spacecraft up and do some testing. Some observations of celestial objects and some commissioning testing of all the instruments to check them out, to make sure they're still performing and they'll be ready to go when we finally get to Pluto in July of 2015.
Ready to answer some of science's most fundamental questions.
The delivery of organic material and water from the outer solar system to the inner solar system may have played a pivotal role in the formation of life on the Earth.
It's just one of many questions about the solar system and its formation that scientists hope New Horizons will help answer. But above all, when New Horizons arrives, astronomers are expecting the unexpected.
I think the most exciting things that we're going to learn from New Horizons are all those things that it never even occurred to us to ask. And suddenly you go there and you realize, wow, we didn't know anything.
One thing is certain. The arrival of New Horizons will be the astronomical event of the 21st century.
It's a whole new kind of world. It's a planet I think everyone has tried to imagine. It's a frontier world. It's going to be the cover of the Rolling Stone.
And perhaps most fittingly, the spacecraft carries the ashes of the man who started the journey to Pluto almost 80 years ago, Clyde Tombaugh. This is a journey to one of the solar system's most puzzling, most mystifying worlds. Once the 9th planet, now a dwarf planet, an isolated oddity that became one of many. A frozen wasteland that could be home to giant geysers and underground oceans, and even possibly to primitive life. With so many twists to Pluto's story, who knows what surprises lie waiting to be discovered? Waiting for New Horizons' arrival in July 2015.
Stephen Hawking is the world's most famous scientist. He's on a quest to answer the biggest question of all. How did everything in the universe come to exist?
If we find the answer to that, we would know the mind of God.
Hawking's goal is to discover a blueprint for the universe. But he's locked in a battle with a disease that has left him paralyzed. And it's advancing. Can he unlock the secret of creation before his time runs out? Stephen Hawking is one of the greatest thinkers of all time. He's on a quest to understand the moment of creation when the universe is born. 20 years ago, he writes a book on the subject that becomes an international bestseller. It promises that soon he will have a single theory so powerful, it will explain all the mysteries in the cosmos. Why did the universe spring into life? And will it ever come to an end? A theory of everything.
We are getting close to answering the age-old questions. Why are we here? Where did we come from?
His determination to find answers has kept him alive far longer than any doctor predicted.
Stephen has got tremendous determination to solve the problems of the universe. And I think that's one of the key factors which has kept him going all these years.
But he lives his life on borrowed time.
The idea that my father had a very short lifespan was always present. I think it was there every single day.
Hawking will not rest until he unlocks the secret of how the universe came to be.
My goal is simple. It is a complete understanding of the universe, why it is as it is, and why it exists at all.
Born in 1942, Stephen Hawking has always been fascinated by the world around him. As a healthy child, he wonders what made the stars. By the time he's a teenager, he wants to find out where the entire universe came from. In the 1960s, scientists have yet to answer that question. Many believe our universe had no beginning. It is timeless and unchanging. But a new theory gains ground. Everything in our universe exploded from one tiny point, like a shower of fireworks. Scientists nickname it the Big Bang. But how can we suddenly go from nothing to everything in one moment of creation? Just 20 years old, Stephen Hawking's first mission is to find out. In 1962, he's just started his PhD at Cambridge University, where he's eager to prove himself. According to his old friend Kip Thorne,
Stephen was beginning to develop a reputation at that stage, but just barely beginning. It was not at all obvious at that point that he was going to come to tower over all the rest of us.
But it's around this time that Hawking notices he's becoming very clumsy. A visit to the hospital leads to a startling diagnosis. Doctors discover he has amyotrophic lateral sclerosis, or ALS. The disease wastes his muscles. Before long, he will be completely paralyzed. Within 2 years, he will be dead. Hawking is just 21. His dream of unraveling the mysteries of the universe crashes down around him.
I had just been diagnosed with ALS, and I didn't know if I would live long enough to finish my doctorate.
It's the darkest period of his life. According to his daughter, Lucy Hawking,
he became very depressed and very saddened. He was casting around at the time for a PhD topic, but he didn't really see any point in going on, so I think everything seemed very bleak and very hopeless to him.
But then Hawking meets Lucy's mother, and they fall in love, despite his death sentence.
Getting engaged and getting married to her was for him the turning point, that was the event for him that turned him around and gave him hope and made him decide that he was going to carry on.
Hawking sets out to discover the origin of the universe before his time runs out.
Does the universe, in fact, have a beginning or an end? And if so, what are they like?
Scientists remain skeptical that something can come from nothing, as the Big Bang predicts. Hawking wants to find out. His first break comes in 1965. He attends a lecture by a brilliant mathematician named Roger Penrose. Hawking hears something that grabs his interest.
Stephen was in the audience at the back of the room, and he was asking some very pertinent and difficult questions.
Penrose suggests something astonishing. There's a hole in space where huge objects disappear. If matter disappears into nothing, maybe it can also appear from nothing. This could be Hawking's first step towards proving the Big Bang. But how can there be a hole in space? The answer might lie with gravity. Einstein's general theory of relativity says gravity isn't just a force of attraction, it actually bends space. Oxford University physicist Pedro Ferreira studies gravity's impact on the universe.
Well, Einstein realized that gravity wasn't this force that acted between two bodies. It was something much more elegant and beautiful.
Einstein pictures space and time as a fabric. Planets and stars press on this fabric and create dips. In a stroke of genius, he realizes gravity is not a force, but the bends in this fabric. The dips pull objects towards them.
Let's imagine this rubber sheet is space. These glass balls that I'm holding in my hand are planets and stars. Now, if you place a planet or a star in the universe on space, it'll create a dip. And the bigger the object you place, the bigger the dip. Imagine that the Earth is this coin, and I just send it coasting round our sun. It'll settle nicely into an orbit. It's just following the deformed nature of the fabric of space. That's what gravity is, and that's what Einstein realized.
So what we experience as gravity is actually the curve of space-time around us.
The theory of relativity does force us to fundamentally change our ideas of space and time.
When that fabric gets stretched to breaking point, something dramatic happens. A hole in space opens up. A hole down which things can disappear. This chain of events starts when a star dies. It begins to collapse in on itself, getting smaller and denser. If a star 20 times the size of the Sun dies, it has a drastic effect on the fabric of space-time.
If you imagine what this means in terms of the fabric of space-time, you're just pressing down on it incredibly hard. You're pressing so hard on it that at that point, it almost tears.
The depression is so deep that nothing can climb out, not even light. This is known as a black hole.
If this star is big enough, it'll collapse to a tiny, minute point, incredibly dense. And it'll create a dip in space, so deep that if an object tries to pass by, it'll be sucked in, it'll be sucked all the way down into that point. That's a black hole.
Roger Penrose discovers that at the center of a black hole is a point of pure gravity. It's called a singularity.
As you go into a black hole, you will encounter something which goes against the laws of physics as we previously understood it. Roughly speaking, you could say a singularity is where space and time come to an end.
A singularity is like a drain, a hole in space. Everything that falls down it disappears. Hawking wonders if the opposite could be true. According to the Big Bang Theory, all the universe suddenly sprang from a point of nothing. Could this hole be the key to explain how this happened? In a moment of genius, he sees the solution. It's elegantly simple.
I soon realized that if one reversed the direction of time in Penrose's theorem, the collapse became an expansion.
Instead of sucking everything in, a reverse black hole explodes out in a shower of space, matter, and time. Exactly as the Big Bang Theory predicts. Against a sea of skepticism, Hawking proves the universe suddenly appeared from nothing. It sprang from inside a singularity. The debate is over.
The universe must have had a beginning in time. This was finally proved by Penrose and myself, on the basis of Einstein's theory of relativity.
Hawking found the origin of time, but he hasn't found a way to stop it ticking. He's now 26 years old. His disease has advanced up the muscles in his legs. He can no longer walk. But his brain is alive with questions. Hawking now knows a moment of creation happened, but not what caused it to explode into being. This will prove his biggest challenge yet. Can he find the answer before his body collapses? Stephen Hawking has discovered where the universe began. A tiny hole in space, known as a singularity. This exploded in a Big Bang to create everything in the universe. But he doesn't understand what made it explode.
Why are we here? Where did we come from?
To find the origin of the universe, Hawking used Einstein's general theory of relativity. Relativity explains how gravity acts on large objects like stars and planets. But when the universe was born, it was smaller than an atom. So to understand how it grew, he needs the theory of the very small. Quantum mechanics. The trouble is atoms are unpredictable. They don't follow the ordered rules of gravity. The theories of general relativity and quantum mechanics are incompatible.
Unfortunately, these two theories are known to be inconsistent with each other. They cannot both be correct.
At NASA Goddard Space Flight Center, Kim Weaver is interested in the conflict between the theories.
In a way, this ball can be used to represent the tension, or the battle actually, that's going on between general relativity and quantum mechanics, quantum physics. The surface is smooth. It represents a large scale. General relativity, gravity, acts on a very large scale. And we can predict what's going to happen based on those equations. But if we zoom into the quantum world, things are very chaotic, and these larger scale laws don't apply.
We used to think that electrons orbited around the nucleus of an atom, like planets around the sun. But scientists now know that electrons pop up and disappear at random. They can even be in more than one place at the same time. Normally, gravity appears to play no part in this chaotic world. But at the moment of the Big Bang, there was a huge amount of matter held together in a tiny space. So gravity must have had a role.
Bringing these two ideas of general relativity and quantum mechanics together into a unified whole is what Stephen Hawking set out to do.
He wants to combine the two theories into a theory of everything in order to find out what triggered the moment of creation.
If we find the answer to that, it would be the ultimate triumph of human reason.
Hawking knows the theories of gravity and quantum mechanics clash at the instant of the Big Bang. But he believes they also clash inside a black hole. This is where a huge amount of matter crushes to a tiny point. So he returns to black holes to investigate. If he can unite the two theories here, it could help him understand the Big Bang. Relativity says nothing can exist on the edge of a black hole. Everything is sucked in. But quantum mechanics states that space is never empty. It's full of tiny pairs of particles.
Space is essentially empty to us, and it is empty when we look at it. It appears to be empty. But at this very tiny level, it's not at all. In fact, it's filled with virtual particles coming into existence and annihilating each other all the time.
Energy waves in space create tiny particles. Every particle has an antiparticle. One has positive energy and the other has negative energy. These pairs appear, but then collide and destroy each other.
Quantum mechanics was very well established, but no one knew how it played into the larger scale of the universe. And that's where Stephen took those two things and said, let me now play with this in my mind. How does this work? If I put a virtual pair next to a black hole, what happens?
To unlock the secrets of a black hole, Hawking must discover what happens to these particles. Now 28, his body is wasting away, but his mind doesn't let him down. He has a flash of inspiration. The answer lies with the fact that the particles are positive and negative.
And what Hawking realized, what's really fascinating about this, is when a pair of particles like this appears near the event horizon of a black hole, the one with negative energy falls into the black hole, and the one with positive energy escapes as radiation.
The negative particle is pulled into the black hole, but the positive particle has just enough energy to avoid getting sucked in. It's released as a particle of radiation. Hawking has proved black holes give off heat, and these positive energy particles are the source. It's called Hawking radiation. The revelation that something can escape the grip of a black hole shocks the world.
When I first announced the results of my calculations, I was greeted with incredulity. By their definition, black holes are not supposed to emit anything.
Hawking proves that while gravity sucks in the negative particle, quantum mechanics allows the positive particle to escape. The two theories can work together. It's the closest anyone's ever come to a theory of everything. But while the world celebrates Hawking's discovery, privately he is concerned. His theory of everything has a fatal flaw. Stephen Hawking is on a quest to unite the two opposing sides of modern science: general relativity and quantum mechanics. If he achieves it, he will have a theory of everything. One equation that could reveal the underlying plan of the universe. It might even explain how it exploded into being. To find it, Hawking needs to piece back together an explosion that detonated 14 billion years ago, the Big Bang. But how? His starting point is an astonishing prediction. Black holes explode, and in a way that makes them very similar to the Big Bang. Hawking discovered that unlike negative particles, positive particles can escape the gravity of a black hole. Now he takes his theory a step further and discovers that over time, a black hole begins to evaporate like a puddle in the hot sun. Over billions of years, it sizzles away. As it gets smaller, it gives off more radiation. It shrinks faster and faster until it shrivels right out of existence. And at that moment, something dramatic happens.
The most reasonable guess is that it would disappear completely in a tremendous final burst of emission, equivalent to the explosion of millions of H-bombs.
It's this tremendous explosion from a tiny point that grabs Hawking's interest.
The Big Bang resembles a black hole explosion, but on a vastly larger scale.
So Hawking's question is, could anything come out of the black hole when it explodes? If it is similar to the Big Bang, will it release a high-energy stew of particles, like in the early universe?
An understanding of how black holes create particles will lead to a similar understanding of how the Big Bang created everything in the universe.
It could be a mini version of the moment of creation. But all of this is theoretical. No one knows if black holes do explode. Now, for the first time, we may actually see this happening. On June 11th, 2008, NASA launches a state-of-the-art telescope called Fermi. The telescope will search the vast expanse of space for the last gasp of a tiny black hole. As it dies, it should release a huge blast of high-energy particles called gamma rays. That's what Fermi should see. Steve Ritz is the lead scientist.
What we'd be searching for is a tiny object, a microscopic object, no bigger than an individual proton, the core of a nucleus, and yet it's shining apparently like one of the brightest objects in the whole sky.
But Fermi's search for these black holes isn't easy. There's a flood of gamma rays from exploding stars that could mask an exploding black hole.
So here's what the whole sky would look like if you had gamma ray eyes. We'd hope to see the individual black hole at the very end of its lifetime making an explosion. And that could happen really anywhere on this image. And that's why it's so incredibly interesting, because one of those contributions could be the individual primordial black holes producing their Hawking radiation.
Ritz's team continues to search for a black hole explosion caused by Hawking radiation. These events are rare, but the payoff is huge, so the search continues.
It would be incredibly exciting if we discovered a family of gamma ray bursts that had no other explanation than the Hawking radiation from microscopic black holes. It would be a revolution in science.
While Fermi searches for clues to how the universe kick-started into life, Hawking's uncovered a mystery that could derail his quest for a theory of everything. In the moment after the Big Bang, something strange happens to gravity. For some reason, it suddenly changes gear and gets weaker. And this is crucial to our existence today. If gravity hadn't weakened, it would have yanked all matter back in on itself. universe we know today wouldn't exist. The mystery is, why did gravity weaken just enough to stop the universe from recollapsing? Hawking needs to find a way to explain this.
If we want to know what happened when the universe began, we have to have a theory to explain gravity on a very small scale.
Gravity is actually the least understood force in nature. It's much weaker than the other forces. Consider electromagnetism, for instance. Electromagnetism is the force that tears up our skies in violent storms. It also binds atoms together into everything we see around us. At the instant of the Big Bang, scientists think electromagnetism and gravity are the same strength. As the universe expands, gravity dramatically weakens. Sean Carroll is a cosmologist who studies gravity at the moment of the Big Bang.
Gravity is something we notice every day. We drop things. We have to work against it to climb a set of stairs or to move around. It seems to us like a powerful, important force in our lives. So the puzzle is that, in fact, gravity isn't really as strong as we think. I can take something very, very tiny, like a set of keys, and if I drop it, it could smash something far below. Nevertheless, something as small as this magnet can be more powerful than gravity just because the electrical and magnetic forces here are intrinsically more powerful. Just a tiny little magnet is able to overcome the gravitational force exerted by the entire Earth.
Nobody knows why, after the Big Bang, gravity changed gear and became weaker. Hawking's theory of everything should reveal the inner workings of the universe, but it can't explain this. Something is wrong with the blueprint. He sets to work trying to puzzle it out. He now has the top minds in the field working with him. But only a few members of this inner circle can understand his speech. He must painstakingly dictate his scientific papers. The process is slow, but he is making progress. His family worry he is pushing himself too hard.
There was always this terrible, terrible fear whenever anything went wrong, or when he started choking or coughing, or he got an infection, that this was it. Because you just never knew what might happen next.
Then in 1985, on a trip to Geneva, Switzerland, tragedy strikes. Aged 44, Hawking collapses with pneumonia. An emergency tracheotomy saves his life, but severs his vocal cords. Unable to communicate, completely cut off from the world, Hawking plunges into his own black hole. 6,000 miles away in Lancaster, California, speech software designer Walt Wolters gets an urgent call from a friend about a new client.
He mentioned that he was a physics professor at Cambridge. I said, gee, that sounds like Stephen Hawking, you know, and he said, well, I'm not allowed to say. And I said, well, I'll tell you what, if it is, I'll donate whatever he needs.
Hawking is able to make a slight movement with his fingers, so he can use a switch. Wolters designs an ingenious system that helps predict the words Hawking will use.
I choose the letter B, and I'm going to choose the word black here. Now, after I selected the word black, and in Stephen's case, the word black is almost always going to be followed by the word hole. Now, if I want to speak that, I can just choose the speak command here.
Black hole radiation.
Wolters sends the machine to Hawking, and the voice we hear today is born.
I like my present voice, even though it has an American accent.
It's the breakthrough Hawking needs to carry on with his work.
The first time I came back to see him after the initial time, he was scanning at 10 steps per second. This is blinding speed.
He'd sort of risen like the phoenix from the ashes to be this new character with an American electronic voice. And he's so sort of good-humoured about it that you just felt admiration, I suppose.
Never in these circumstances have I ever seen him show frustration. He just keeps going at it.
Hawking returns to Cambridge and click by click presses on with his work. He employs a team of graduate students to help with the computations. He's been given another shot at cracking the theory of everything, and he's more determined than ever. Stephen Hawking has spent 3 decades trying to discover a theory of everything, a powerful set of laws that governs the entire universe, from the tiniest particle to the largest galaxy. It's been the holy grail of theoretical physics for over a century. Hawking painstakingly lays the groundwork for this theory, but he could be beaten to the finish line by a radical new theory, string theory. One of its architects is physicist Michael Green.
It represents such a profound change in our way of thinking of the universe, both in the very small and in the very large, that it should have all sorts of repercussions.
String theory could even be a candidate for the theory of everything. It unifies every single thing in the universe, from atoms to stars, planets to people, because they are all made from one ingredient, strings. Strings are so tiny, there's no way to see them directly. Equations show they could be a trillionth the size of an atom. To get an idea of how small this is, imagine an atom blown up to the size of our solar system. The nucleus would be the size of our sun. But even in this scaled-up world, strings are tiny, smaller than the Earth, smaller than the smallest state, about as tiny as one person in our entire solar system.
I would be the size of a string.
Strings are the building blocks of everything we see around us. The entire universe is a gigantic mesh of these vibrating strings.
We're all made of string, and we're moving in a stringy space-time, and everything is stringy.
To correctly describe our universe with string theory requires something incredible. The world we see around us is made up of 3 spatial dimensions: width, height, and length. But Green and his colleagues think that we are actually surrounded by at least 9 dimensions. This may sound like science fiction, but Green suspects these extra dimensions are hidden from our view.
Clearly, since we don't see these extra dimensions in everyday life, they must, in some sense, be very small and not directly observable.
Green collaborated on his theory with Caltech physicist John Schwartz.
We have the perception that we live in this 3-dimensional world, even though it may in fact be more dimensions.
But how can there be dimensions that we haven't noticed?
This is a line, which is a 1-dimensional object. But if we turn it around and look inside, we can see that it's actually a rolled up piece of paper, which is a 3-dimensional world. We can see that there's an inside, and if we put an ant in here, the ant can go around in 3 directions. So the ant sees it as a 3-dimensional world.
The extra dimensions reveal themselves if, like this ant, you're small enough to see them. Schwartz believes these extra dimensions are curled in on themselves, curled up into tiny knots that are so small we can't see them.
But the fact that we don't see them doesn't mean that they don't have a profound effect on the universe we live in.
Schwartz and Green believe these extra dimensions explain why gravity is so weak. They believe at the moment of the Big Bang, gravity is strong, but then the universe expands. Gravity spreads out into the extra dimensions, weakening as it goes. This explanation removes the final stumbling block to the theory of everything.
Let's consider an analogy in which gravity is like music. When I'm close, it's loud, and as I walk away, it gets quieter.
The music disperses in different directions. As it does so, it weakens.
Here, the music is almost inaudible, and that's because it's spread out over space. Now imagine, instead of music, that we're talking about gravity, and imagine that there are extra dimensions in space. Extra dimensions in which the gravity can spread out even more.
More dimensions in space mean more directions to spread across. This in turn makes gravity even weaker. String theory explains how the universe we see today exists. After the Big Bang, as the universe expands, gravity spreads out through these tiny extra dimensions and weakens. Gravity weakening is what stops the universe from collapsing back in on itself. It's the missing piece in Stephen Hawking's quest for the theory of everything. He concedes that Green's string theory is the best contender to explain how the universe came to be.
Stephen Hawking's relation to string theory is very intriguing. I think he's a big admirer, but not necessarily a believer. His ideas have had a profound influence, actually, on many things that have happened in string theory. And with a bit of luck, string theory has had some influence on his ideas as well.
We believe that there is one fundamental theory that describes dimensions that are curled up so small that we don't notice them. Nevertheless, these hidden dimensions affect physical quantities like gravity.
One hitch is that none of this has ever been proved. String theory and the extra dimensions exist only on paper. Like so many of Hawking's own discoveries, there is no proof. But that might be about to change. And the earliest moments of the universe could soon be revealed. This is the CERN laboratory in Geneva, Switzerland, home of the Large Hadron Collider, the biggest experiment ever built. Deep below ground, scientists are attempting to recreate the conditions that existed just after the Big Bang, to reveal how everything around us came into being. Scientists will search for clues to what happens in the high-energy environment, like the one that followed the instant of creation. It's the moment Stephen Hawking has been waiting for.
Why is the universe the way it is? A new window on the very early universe will be opened.
Scientists will fire subatomic particles in opposite directions. The particles will travel for almost 17 miles, accelerating to close to the speed of light. Then they will slam into each other with a force trillions of times more powerful than dynamite. This high-energy collision will produce particles similar to those in the aftermath of the Big Bang. It should reveal the key ingredients of the universe, and possibly the recipe behind them. The Large Hadron Collider will take us as close as humanly possible to the moment of creation. And in an incredible one-two punch, it could prove that both string theory and Stephen Hawking are right. String theory predicts that we are surrounded by tiny extra dimensions. These extra dimensions trap gravity. If this is true, particles colliding in a small region could feel ultra-strong gravity. This could trigger matter to collapse on itself into a mini black hole, exactly as Hawking predicts. So rather than a Big Bang machine, the collider could become a black hole factory.
The black hole might actually grow because over time, the black hole will pull material into itself. It could grab onto molecules in the atmosphere. So its mass will increase. I have no idea what will really happen in that case, but that means that the experiment does need to be controlled well.
Researchers estimate it's theoretically possible. They could create mini black holes at the rate of 1 per second. Some people fear that just one black hole could swallow the Earth. It's a terrifying thought. Scientists at CERN, however, are putting their faith in Stephen Hawking. Hawking predicts that small black holes will evaporate. They should burn up almost instantly, lighting up like a Christmas tree.
They will produce little black holes, which will then radiate and decay and disappear, according to Stephen Hawking predicted many, many years ago. And that would be, of course, truly exciting.
If black holes do appear, it will reveal the secret of why gravity weakens after the Big Bang. Tiny extra dimensions in space.
If they found proof of extra dimensions, I would be completely staggered. It would be extraordinary, because we would have finally found that space had more than 3 dimensions, which is fundamental.
A fault in the complex machinery delays the big startup until spring 2009. Even then, it may take years to comb through the data for proof of extra dimensions and tiny black holes. After searching for a theory of everything for almost half a century, Hawking desperately wants to live to see the culmination of his life's work. So once again, he faces a battle against time.
There are grounds for cautious optimism that we may now be near the end of the search for the ultimate laws of nature, though much more work will be needed.
Stephen Hawking is nothing if not a fighter. He has taken on the biggest mysteries in the universe and cracked them. He found the birthplace of the universe. He forced the two opposing sides of modern science together to prove that it is possible to escape a black hole. An achievement he has mirrored in the battle with his disease.
The greatest thing I've learned from my dad is if you fall into a black hole, don't give up. You can get out of it again. And that's so clearly what he's done with his life.
Hawking has outlived his death sentence by over 40 years to become one of the longest surviving sufferers of amyotrophic lateral sclerosis in the world. But questions remain, and a single equation powerful enough to describe all of existence still eludes him.
Stephen's grit, his stubbornness, have contributed to his continuing vigorously ever so much longer than anybody ever expected. And I'm hopeful that he may still be around working on this 20 years from now.
Stephen Hawking is as determined as ever to find a definitive theory of everything for our universe.
Planet Earth, 4.5 billion years old. A solid ball of rock weighing 6 trillion tons. We are on a quest to destroy it. Using cutting-edge physics and planetary science, we will explore what could destroy our planet completely. A black hole?
It might seem harmless, but its gravity is strong enough to destroy the entire planet Earth.
A collision with the sun?
And before you know it, the Earth is falling into a fiery plummet.
A huge antimatter bomb?
Poof, okay, at a huge annihilation.
A giant rock from space?
You wouldn't want to be standing here 50,000 years ago.
Or perhaps a swarm of self-replicating robots.
It's been a nightmare of sci-fi.
These ideas may sound like science fiction, but they're all grounded in proven scientific fact. Our planet is seriously tough. It has survived everything a hostile universe could throw at it for 4.5 billion years. Yet in the past few decades, we have developed technologies so powerful that some people fear we could literally destroy the Earth. It's time to find out if they're right. 6 top scientists are about to reveal what it would really take to destroy an entire planet. Our first candidate is a black hole, the greatest destructive force in the universe. A black hole is what's left when a giant star collapses in on itself. The result? Gravity so strong that nothing can escape, not even light. Soon, we may be able to create black holes right here on Earth. Physicists use huge particle accelerators to try to recreate what happened after the Big Bang. But when they smash particles together, they also risk creating a black hole. Think of a black hole as Niagara Falls, and the water going over like space getting sucked in. This unfortunate kayaker has gotten too close. Just like a star getting too close to a black hole. Dr. Phil Plait, astronomer and author.
The water going over the lip of the waterfall is just like space itself falling into a black hole. If you're kayaking, no matter how fast you paddle, once you go over that lip, you're going down. That's the point of no return. And it's the same thing with a black hole. No matter how fast you try to get out, it's going to take you down.
The gravity in a black hole is fundamentally different from the gravity we experience in normal life. Normal gravity you can escape from, at least in theory. Cosmologist and golfer Professor Lawrence Krauss.
It's commonly said that what goes up must come down, but that's not always the case. For example, if I hit this golf ball here and I hit it well, it would go fairly far, but it would still come back down to Earth. If I hit it harder, it would go further and still come back down. But if I hit it with a speed of 5 miles per second, it would escape from the Earth's gravitational field.
But for the ball to escape from a black hole, it would have to move faster than the speed of light, and that is simply not possible. What goes into a black hole, planets, or even stars, never comes out. Our small planet wouldn't stand a chance. For anyone looking for a way to destroy the Earth, black holes are a good place to start. The trouble is, there are none close by enough to do the job. Unless we make one. That's where the atom smashers come in. With a lot of math and a gigantic machine, physicists can now generate atom-sized explosions that may be powerful enough to create microscopic black holes. They are trying to study the Big Bang. The force of the impacts recreates the particles that made up the universe in its earliest moments. Some of those particles may create microscopic black holes. That doesn't mean our planet is doomed. In theory, black holes this small would just evaporate like tiny soap bubbles. To destroy this, you need something bigger.
Black holes come in all sorts of different sizes. For example, at the center of our galaxy, there's a black hole of 1 million solar masses. If you took the mass of our sun and compressed it down to be a black hole, it would be the size of a large American city like Phoenix here. On the other hand, if you took something like this mountain here, which is maybe 1 million tons, and made it a black hole, it would be smaller than the size of a single atomic nucleus.
Somewhere along that scale, black holes get powerful enough to cause serious damage. To destroy the Earth, it turns out you need a black hole that weighs about the same as the Earth. The Earth is 8,000 miles across. But a black hole weighing that much would be the size of a marble. Professor Clifford Johnson, physicist.
Here I have a marble-sized black hole. It might seem harmless, but its gravity is strong enough to destroy the entire planet Earth. What would eventually happen is that it'll start sucking things in, slowly at first, and then it will grow in size. It will grow and grow and grow until it swallows the whole Earth.
To imagine what that marble would do to the Earth, picture what it does to a physicist.
The gravity is much stronger on one side of an object closer to the black hole than it is on the other side of an object, producing an effect that's called spaghettification, as that object is stretched out and pulled apart as it falls into the black hole.
A big enough black hole could do this to our whole planet. There's no way even the most powerful atom smasher could make a black hole this big. To destroy the Earth, we need to find one ready-made. Astronomers think there are 10 million or so black holes in our galaxy. If one of them strayed into our neighborhood, it could rip our planet to pieces. Earthbound telescopes may not even detect it. Humans would only know it was approaching when its immense gravity triggers huge floods and earthquakes. As it plunges into our atmosphere, the black hole acts like a vacuum cleaner, sucking with a force over 1,500 times Earth's gravity. Then it begins to distort the shape of the whole planet. Earth's surface stretches and tears apart. Finally, the hole hits and flies straight on in, heating and vaporizing matter as it goes. It starts to orbit the Earth, inside the planet itself. all the time devouring everything in its path. Gradually, the orbit slows. The black hole spirals down into the Earth's core. Eventually, it eats the entire planet. All that's left is the black hole itself. It's a devastating end for planet Earth. But fortunately for us, it's unlikely ever to happen.
If you want to destroy a planet, a black hole is a great way to do it. But the problem is, it depends on the kind of black hole. A microscopic black hole would just pass right through the Earth, and it really wouldn't do that much damage. A black hole with the mass of the Earth would be about the size of a marble, and that would do a considerable amount of damage passing through the Earth. But again, it might not destroy the planet. If you want to do the job right, you need a stellar mass black hole, something with about 3 times the mass of the Sun. That thing would come in and it would tear the Earth apart and gobble down the pieces, and it would be game over. The problem is, we don't know how to make any of these black holes. Technologically, we just can't do it. And with a naturally existing one, we don't know how to move them. So there's got to be a better way.
So if black holes don't work, time for a new approach. One surefire way to destroy the Earth is to change its distance from the Sun. Move the planet closer and it bakes. Move it out and we freeze, sending us into another ice age. Scientists have recently begun to realize that moving a whole planet might actually be possible. In fact, we use the same principle to slingshot space probes round the solar system. Planet Earth could be just a few well-placed flybys away from a fiery death. What would it take to incinerate an entire planet? Answer: a nuclear furnace nearly 1 million miles across. It sounds crazy, but the truth is this will happen. It's just a matter of time.
As the sun gets older and older, it's going to actually get brighter and brighter. And within about 2 billion years, the Earth will be in an uninhabitable zone. It'll be like Venus. There'll be a runaway greenhouse effect. All the water on Earth will be destroyed, and the surface temperature will be about 1,000 degrees.
Eventually, the sun will swell and scorch the Earth, unless we somehow move the Earth away from the sun to save it.
Alternatively, if you were sufficiently evil, I suppose, you could imagine doing exactly the opposite. Harnessing sufficiently large objects to transfer gravitational energy to kick the Earth's orbit closer to the sun.
Easy to say, not so easy to do. The Earth weighs in at 6 trillion tons. Pushing something that big is quite a challenge. But there is a way. It's called gravity assist. Space probe engineers use gravity assists all the time. Take Saturn's Cassini-Huygens probe. It's the size of a school bus, one of the biggest probes ever built. To build up enough speed to fling the probe out to Saturn, it had to swing by Venus twice and Earth once. Each flyby stole energy from the planet and added it to the probe. The probe got a lot faster by altering the planet's course just a little.
The name of the game, we take a rock about 1 mile or 2 across and we move it so that it just passes the Earth the right way, and it'll steal energy away from the Earth. The asteroid will go flying off and the Earth will move in toward the sun. But we shouldn't just waste the asteroid when we can recycle it. If we're clever, we can take the asteroid and have it go toward the planet Jupiter. And then if we pass Jupiter in just the right way, it'll take that extra energy it stole from the Earth, give it to Jupiter, and then fall back toward the Earth. And if we aim everything just right, we get a conveyor belt of energy. We steal it from the Earth, give it to Jupiter, and then come right back. And in fact, we can use hundreds or even thousands of asteroids this way, continuously stealing Earth's energy and dumping it toward Jupiter. And before you know it, the Earth is falling into a fiery plummet.
First, you need to catch an asteroid. It's as big as a mountain, and it's traveling around 10 miles a second. Next, you need to attach rockets and boost the asteroid onto the perfect course. Next, repeat, thousands and thousands of times. Very slowly, over thousands of years, the Earth will fall towards the Sun. Right now, we're just over 90 million miles away. By 70 million, the Earth is a superheated desert like Venus. Then things start to get really bad.
As the Earth slowly spirals into the Sun, a series of events unfolds which unfortunately spells doom for our planet. As the Earth approaches the Sun, the atmosphere heats up and blows off, and the oceans boil, basically turning the Earth into a giant comet. But there's worse to come. As the Earth gets closer to the Sun's gravity pulls on the near side of the Earth more than it pulls on the far side, and the Earth stretches like putty. At some point, it gets close enough to the Sun that the Sun's gravity can overwhelm the Earth's gravity, and it shatters, pulverizes our planet.
The Earth is dead, but its ghost could remain, a faint ring of material around the Sun. Peter Schultz, planetary impact geologist.
If the Earth or any object gets too close to another object like the Sun, eventually the tides will rip it apart. As that happens, it would simply be broken into many small pieces that would then encircle the Sun as if it were a ring.
The Sun would resemble Saturn with its own faint ring of rocks and dust. A fiery death and a ghostly remnant. If you want to destroy a planet, this could be the way to go.
A great way to destroy the Earth is to drop it into the Sun, let it plummet to a fiery death. And we can do this. All you need to do is to pass enough asteroids near the Earth in succession to gravitationally drop it into the Sun. And we have that technology. We know how to move asteroids. It's just a matter of getting them on a precise enough orbit to be able to do it.
Maneuvering billion-ton chunks of rock with pinpoint precision at hundreds of miles a minute is quite a stretch. Not to mention the amount of time it would take to capture enough asteroids. We've tried to crush it and burn it. It's time for another plan. An antimatter bomb. Physicists have been searching for over a century for a theory that unites our understanding of the large-scale universe, planets, galaxies, and stars, with what we know of the subatomic world, electrons, protons, and quarks. Their theories are bringing to light some pretty destructive phenomena. One of them could be a world killer. Antimatter. Theorized in the 1920s, detected in the 30s. Now we can create antimatter in modern particle colliders. And the base ingredient for the biggest explosion possible. Antimatter is the most explosive substance ever found. Pound for pound, it's far more powerful than even a hydrogen bomb. But antimatter is hard stuff to find. Everything we see around us, out to the most distant galaxies, is matter, created 13 billion years ago in the Big Bang. It created antimatter too. They look similar. In fact, they are entirely opposite. Put them together, and they wipe each other out. Cosmologist Lawrence Krauss.
Now I have a proton here, and Anti-Krauss over there has an antiproton. And when we bring them together, we're going to make an incredible explosion. Okay, let's annihilate.
This is what happened to all the antimatter created in the Big Bang. It annihilated. If we want to use some for a bomb, we need to make it ourselves. Making antimatter is a bit like firing a gun at a target.
If I shoot a gun at a paper target, the paper that flies out of the target is like matter, and the hole that's left behind is the antimatter. It takes energy to create a matter-antimatter particle pair. In the shooting range analogy, the bullet provided the energy.
In reality, the gun is a particle accelerator, like the one at CERN in Switzerland. Fire protons in a giant tube, steer them around with powerful magnets, use the same magnets to accelerate the protons to near the speed of light, then slam the beam into a block of metal. For every million protons that hit, you get one antiproton. It's as if Plate's handgun only left a hole once in every million shots.
In an accelerator, you only get one particle-antiparticle pair out of every million collisions or so. And so it's really hard to find that one antimatter particle floating around. It's a lot like coming to Niagara Falls and trying to get that one particle out of all the mist. And that's why it's so hard to create antimatter on a large scale.
Assuming we can obtain enough antimatter, the next challenge is to make it into a bomb. Nothing is more unstable than an antimatter bomb. You have to find a way to hold the antimatter without it touching any ordinary matter. If it does, it will explode.
So I have a bunch of antimatter above my hand here. Well, it better not touch my hand, because if it does, poof, okay, at a huge annihilation. But worse, it can't interact with the air around it, because the air is made of matter. And again, you'd get an incredible explosion.
Researchers need a special container to study antimatter. And this is it, a penning trap. Powerful magnets suspend the antimatter in a vacuum.
So if I want to store this antimatter, what I have to do is somehow keep it levitated above my hand, which means I'd have to produce huge magnetic fields in just the right way to keep the charged particles in the antimatter from touching my hand. But I'd also have to store it in an incredibly high vacuum, because any air in the container would again cause an explosion. And so the energies and technology required to produce those magnetic fields, keep that ultra-high vacuum, would mean that you wouldn't have a small object. You'd have to surround it with massive amounts of machinery.
Yet for all that trouble, an antimatter bomb isn't just theory. We can make antimatter, we can capture it, and we can store it. But where do we plant it for maximum effect? If we want to destroy the whole planet, the bomb has to go off near the Earth's core. That's nearly 4,000 miles straight down, further away than London from DC. Right now, that's impossible. The deepest man-made borehole stops at just 7.5 miles. But what if we could? So far, mankind has managed to create a grand total of 20 nanograms of antimatter. That's 100 million times lighter than a dime in your pocket. So the bomb is going to be too small even to see.
Well, 200 feet away in this test range in Arizona, we have the explosive equivalent of TNT. So let's see how big of a bang that makes. Wow.
20 nanograms of antimatter makes quite a blast, but it's way short. To destroy planet Earth, we would need 2.5 trillion tons of the stuff. That's a bomb the size of Mount Everest, at the bottom of a hole 4,000 miles deep. If it were possible, the result would split the Earth into thousands of pieces. With a powerful enough bomb, the pieces would fly out into space and are lost. With a slightly weaker bomb, the pieces fall back under the force of their own gravity, collapsing into a molten ball. An eerie echo of Earth's creation 4.5 billion years ago. It could happen, in theory, but there are a few technical details to iron out first.
So what's the matter with antimatter? Well, if you're trying to destroy the Earth, it'll work, it'll do the job. The problem is you need about the energy that the sun puts out in an entire week. So it's a huge amount, and we just don't have the technology to create that right now.
At the present rate of production, making the bomb would take more than the age of the universe.
The other problem is getting it to the Earth. How do you do that? Well, you'd have to get it to the center of the Earth, and that means digging a hole several miles across and 4,000 miles deep. So in the end, don't think antimatter is probably the most efficient way of destroying the planet.
So, as a way of destroying the Earth, maybe antimatter has some problems. But we know the next approach works, because it already happened once before in Earth's ancient past. Space is a dangerous place. It's full of debris. Rocks the size of pebbles up to rocks near the size of a planet. There are impact craters everywhere, including our moon. These asteroids can hit us as well. An asteroid wiped out the dinosaurs. Maybe a bigger asteroid could destroy the planet entirely. Meteor Crater, Arizona. Almost a mile across, nearly 600 feet deep. Today, science can reconstruct what happened here thousands of years ago. Dr. Dan Durda, planetary scientist.
You wouldn't want to be standing here 50,000 years ago. This iron meteorite, about the size of a small office building or so, it's made out of stainless steel from space. It's about to strike the desert with an impact energy of somewhere between 1 and 10 megatons. And it's that energy that's going to excavate and open up this crater behind me, which is nearly a mile across.
The impact ultimately devastated an area the size of New York City, with 600 times the power of the Hiroshima bomb. And that was small. 65 million years ago, a real monster struck. It was 6 miles across. Sat on the ground, it would outtop Everest by half a mile. The crater was over 100 miles wide. The impact wiped out the dinosaurs and destroyed most of life on Earth. An even bigger space rock could destroy the planet. We're already developing technologies to protect against future impacts. Ironically, you could use those same technologies to make an impact happen. One approach is to hover a space probe near the asteroid. The probe's mass generates a tiny gravitational pull on the rock. Over time, that can change the asteroid's course enough to miss the Earth, or to guarantee a hit. Another protection technology that we could use is a technique called solar sublimation. This diverts an asteroid or comet using nothing more than sunlight. To demonstrate the effect, Dirda starts by building a homemade comet.
Some fraction of near-Earth objects are comets, so let's examine what comets are made of. Let's actually make a comet.
Take some soil, add dry ice, then water, and some chocolate.
We'll put in a few percent of organic material into our comet. And of course, in the outermost solar system, there's a little bit of ammonia here and there. We'll let that be represented by this ammonia cleaner. Let's see if we can pack this up and make ourselves a little comet nucleus.
A magnifying lens completes the apparatus.
If one were to actually focus the light from the sun onto the surface, one could cause some of that water to vaporize away. And just like on this comet nucleus, the jetting action of those evaporating gases act a little bit like little artificial rocket motors attached to the object. And over time, they really do cause it to be pushed slightly off course.
The power of sunlight alone is enough to divert a space rock onto a collision course with Earth. But solar sublimation may not be effective on an object big enough to pulverize our planet. To destroy the Earth, our space missile needs to be big. Like Mars big. We know this for certain because it's happened before. 4.5 billion years ago, a rock the size of Mars struck the Earth a glancing blow. The impact debris created the Moon. If it had hit head-on, none of us would be here. We've come here to the vertical gun range at NASA Ames in California for proof. This 12-foot gun fires beads up to 4 miles per second, 6 times faster than a rifle bullet. Professor Peter Schultz, a planetary impact geologist, uses the gun to simulate a Mars-sized object, represented by this small projectile, hitting our planet head-on. The Space Environment Chamber is ready. Schultz makes his final adjustments. But will our scale model Earth break apart completely?
That hurt. That really hurt. Look at this thing just This is worse than a science fiction movie. That's just glorious disaster. There's nothing left.
A head-on strike, destruction guaranteed.
So the things that destroy an object is going to be a combination of the size of the object, the speed of the object, and the angle. The lower the angle, the less likely it'll completely bust it apart. So to really destroy the Earth, you need something that's humongous and needs to hit straight on.
Now we know what it takes to use an impact to destroy planet Earth. Asteroids and comets are just too small. We need to move something the size of a planet onto a collision course. That's a level of technology we won't be reaching anytime soon.
Now, we can move asteroids around and we can move comets around, but those are only a few miles across. The problem here is that we need something really big. Mars is about 1/3 of the size of the Earth, and even that hitting the Earth won't destroy it. We would need something almost as big as the Earth itself, something like Venus. And even then, we just don't have the technology to be able to move something that big with that kind of precision to aim it at the Earth and blow it up.
Destroying the Earth with a space rock just isn't gonna happen. Perhaps the killer punch won't come from space, but from right here on Earth. Genetics, robotics, nanotechnology. Researchers hope machines will lead us to a brave new world. Already, robots can learn, build other robots, and cooperate with each other. It could be the beginning of a new age. It could also be the beginning of the end. Right now, we can only build robots that work with humans in control, but science is working towards machines that can think for themselves and even reproduce. Robots that can make copies of themselves without human control could one day take over the world. Hod Lipson, professor of robotics. Lipson is a pioneer in robot replication.
If this robot could make another robot identical to itself, and then those two robots can make 4 robots and so forth, these robots could fill up a space such as this here fairly quickly.
Once the first replicate is made, there's no stopping the process. But first, we've got to make them. At Cornell's robotics lab, Lipson and his team already make robots that learn, robots that build, and robots that build themselves. This is the world's first self-replicating robot. Supply it with building blocks and it assembles them to make a copy of itself. It needs Lipson and his lab techs to keep it stocked with plastic cubes. So this robot is pretty benign. To destroy the Earth, we need to develop robots that use smaller blocks and eventually individual atoms.
We've been trying to make robots made of much tinier cubes on the order of 0.5 millimeter, and you can barely see them. There's about 10 of them in this container here. We're trying to get these very small units to combine together, and the smaller they get, the faster and more easy it is to replicate.
Lipson thinks that advances in robotics will revolutionize design and manufacture. But where there's progress, there's also danger. In theory, nano-sized machines could start to replicate out of control. Self-replicating nanomachines could, in theory, destroy all life on Earth. To destroy the planet itself, we need something more. To reproduce, a robot needs energy and raw materials. In other words, food. The more food there is, the more copies our robots can make. And the biggest source of food on the planet is the planet itself.
The ultimate kind of self-replicating process is something that's inspired by nature. So if we can have a machine that can essentially self-replicate using resources in the environment, food and energy, then that would be a pretty big achievement.
And the biggest natural resource on Earth is rock. Design a self-replicating robot that feeds on rock, and it has 6 trillion tons of food right under its feet. Some living creatures already use rock. Rock-feeding bacteria live in the Earth's crust, even several miles deep. But nature's rock eaters are good for the planet. They help form soil and keep life ticking.
There's a whole suite of rock-eating bacteria that we've now uncovered on the Earth, which will go and chew up and eat and use the materials in the rocks for their sources of energy and for the sources of compounds they use to build other biologic molecules. There are literally biologic organisms that do just this, eat rock.
Rock-eating, self-replicating robots. But they've got to be smart. They need to cooperate. Professor Alan Winfield, roboticist in charge of the Cimbrian project, to design robots that swarm like insects.
Cimbrian is a 5-year project to try and build a swarm of self-assembling robots. Perhaps as many as 30 or 40 will physically join and then behave and act as a single organism. The big challenge is going to be how to get the robots to first of all decide what to be, a foot bot, or a knee bot, or a sensor bot, or a brain bot, and then work cooperatively so that, for instance, the organism can stand up and walk.
We can already make robots that reproduce. We can make robots that cooperate. Put them together, and at last we may have our planet killer. Here's the math. Say each robot takes 1 day to replicate. Then after a single month, you have over 1 billion robots. After a year, you have trillions. Earth is covered with machines that do nothing but gobble rock. In the end, no more rock, just a huge ball of self-replicating machines.
Now, what are robots made of? Well, iron, magnesium, aluminum, and silicon. The same thing the Earth is made of. And so all you have to do is create one of these self-replicating robots and let it out into the wild. It'll make a zillion copies of itself, and they will consume the Earth, and eventually there'll be nothing left.
Success at last? Perhaps not. In our quest to destroy the planet, we've tried devouring it, incinerating it, pulverizing it, blowing it up, and breaking it down. Planet Earth is a proven survivor. It has taken everything the universe can throw at it for 4.5 billion years. And one thing is certain, we're still here.